So hello and welcome to this Arrow lecture. Today we're going to be talking about materials for challenging environments, talking about nuclear materials with specific focus on generation 4 fission. So this is kind of our next generation fission power plants, so the next type of reactors that we could use with trying to alleviate some of the current problems with our current nuclear power. So again, I'm Dr. Sandy Knowles. I'm a UKRI Future Leaders Fellow. I'm an Associate Professor at Nuclear Materials at the University of Birmingham in the UK. I'd like to thank again Arua for inviting me to give these lectures, and also to GCRF and UKRI for supporting this initiative.
So last session we were talking quite a lot in detail around the background for why nuclear might be important, and what the fundamentals of the current nuclear technology that we use, what I would call kind of generations 1 to 3 fission. So over 60 years plus of development, nuclear reactors have come a long way. They are incredibly safe now, but there's still things that we might consider we might want to improve. So last lecture we talked a bit around safety, we talked about cost, we talked about waste, in terms of to what degree we view that as a problem in current reactors, and I think maybe different people have different thoughts in that regard, but ultimately there is a public acceptance problem for nuclear around safety, cost, and waste. And as nuclear engineers, we need to do as much as we can to solve any of those problems where we can see them, and also rationally explain how serious they are compared to other technologies. And I think nuclear and many energy technologies are often considered in isolation. And I always have to kind of bear in mind that coal and fossil fuels are bad, and it's a relative, pick your poison. But in this sense, I think nuclear really has many advantages we might like to employ, certainly compared to the alternative technologies. Ultimately, it's proven. I think in our energy crisis, we need proven technologies. But I think there's still more we can do. And as scientists and engineers, then we want to kind of always push the envelope and improve things yet further. So this is kind of a lot of what Generation 4 fission really seeks to address, is to say, okay, well, these are the public acceptance concerns for nuclear. Can we yet further improve them to a point where they can be accepted? So in Generation 4 fission, we have ideas around further improved safety. And particularly we have this idea of walk-away safety. So when we look at kind of different nuclear accidents that have happened, every industry has accidents. And the key thing is that we need to learn from those accidents and make sure that we don't repeat the same mistakes. And so in Generation 4 fission, most of the designs utilize processes that don't need, for example, the constant replacement of cooling water, or they don't need an operator to actively flick a switch or turn on a pump or something, or that there's no power redundancy issues. And so in this, you can have a reactor core design that will self-shut down in a safe manner. If there isn't a kind of thermal runaway concern or anything like that, you don't have to operate cooling pumps. So there's walk-away safety. One of the ideas and ambitions is around reduced cost. Typically, this is often really through the route of increased efficiency. And the idea here very often is to increase the operating temperature of the reactor. So if you increase the operating temperature, then you increase the thermodynamic efficiency of the steam part of the energy extraction. So if you look at thermodynamic efficiencies and the kind of thermodynamic profile for say, a steam turbine, as you go up in temperature, the same argument applies for a gas turbine in a jet engine. It is as you go to higher temperatures, you get increased fuel efficiency. And so the idea is if you can increase the fuel efficiency, then you can reduce the cost. We also then want to look at reducing the waste. So depending on the reactor design you choose, well, firstly, by increasing efficiency, you're going to reduce waste. But also there's some technologies we could use which would actually help burn up prior waste. So we could use it to help the fuel reprocessing angle as well. So we could kind of call these burner reactors. I think what's also really interesting in terms of new energy applications. So we mentioned a bit around this idea of cogeneration. I think many reactors, but particularly Gen 4, are particularly well adapted to to deal with just load following, which was kind of the baseline that we would expect of any reactor now. But we need to kind of probably go further than that. And particularly when we start talking about decarbonising the energy grid, within 10, 15 years, I think we're going to achieve that. That's quite an easy win in terms of decarbonisation. But decarbonising electricity is not decarbonising fully. So to go to net zero, we need to decarbonise industry. We need to particularly decarbonise what we call process heat. So many chemical processes, I think it's probably a third or a half of energy usage, similar quantity for electricity, or even more is in just heating things. And typically we do that just by burning fossil fuels. So one example would be in steel production, for example. And so one of the ideas is, could you use the heat generated by the nuclear reactor, particularly if you go to higher temperature reactors, that would really open up many opportunities to decarbonize industry. So if you could use the heat directly. And this is something that really was considered even sort of 50, 60 years ago, to kind of co-locate, say, aluminium smelters with nuclear power plants. There's been lots of kind of attempts and considerations, and definitely as we improve technology and can get the finance to work out, there's many opportunities there. The other one that's kind of coming more into the fray is hydrogen production. So if you want to produce hydrogen very efficiently, you can do that through reactions that happen at high temperatures. So if you go to kind of 800 degrees C, you get new chemical reactions unlocked that would really greatly improve the economics of creating green hydrogen. So that's one of the areas I'm particularly interested in working in myself, to try and see, could we use these new high temperature reactors in order to generate hydrogen, green hydrogen, without any fossil fuels. So there's multiple reactor concepts that are being pursued towards next generation fission reactors. So we have this range of ones that we're going to kind of spend a bit of time talking about one by one today. So this is kind of the first section of this lecture, talking about the reactors themselves. So this is kind of setting what the demands might be, and then we'll talk a bit more about kind of the materials that are being considered. So the first one we're talking about is a supercritical water reactor. So to a certain extent, just keep dialing up the heat. Why not just take very similar technology compared to what we've got today and just increase the temperature while still using water as our coolant and as our moderator. And so there's a few different designs that are going down to try and achieve this. I guess you've got issues in terms of the pressure versus boiling of the water and where that is occurring. And as you boil off the water, what does that mean for your neutronics? So there are some kind of interesting challenges there. It doesn't necessarily make it trivial to just increase the heat of the reactor. I mean, that's quite easy. You just increase the rate of the chain reaction, you generate more heat. That will heat your water to a higher temperature. But it does have its own challenges in terms of neutronics and reactor design. And further, it doesn't necessarily really help us much in terms of the kind of increased safety angle. We're still going to need this idea of quickly pumping water through the reactor. So whilst there are people pursuing this, it's maybe not one of the core Gen 4 technologies. Next one then would be looking at gas-cooled fast reactors. So in the UK we have these. So our AGR fleet are broadly going on this technology. Probably not, again, going to the full temperature capability we might want to go, but I think it's about 500 degrees C, which is significantly hotter than the majority of fission reactors around the world that are typically about 300 or 350 degrees C. So again, now we've exchanged the water for a gas as the coolant medium. So in most of the UK ones, this is carbon dioxide. And you could also consider using helium, which is being considered a lot towards fusion more. Helium is one of the gas coolants you might choose. And so then there's also ideas of, as you go up in temperature, going from CO2 to supercritical CO2. And there's a lot of research looking at, as you go up in temperature, you again have a coolant medium, so your heat transfer medium is gas. I mean, one disadvantage is gases can't transfer as much heat as a liquid, so you have to have much faster flow rates. And also you have some degree of corrosiveness, of carburizing nature of, say, carbon dioxide would be one of the issues. And this is a self-contained loop that is a sealed loop. But otherwise, then you again just go to a turbine and then different technology that is quite well established. Then probably one which is seeing a lot of interest is then into the very high temperature reactors. So really we're kind of wanting to go more to 800 degrees C here. So there's two technologies. There's one which is the high temperature reactor, which is more about 600 degrees, and then the very high temperature reactor trying to go to 800 or even in higher temperatures. In this we are using a helium coolant, and particularly it's the temperature that's the main driving force, and that puts a lot of demands in terms of all your different components within the reactor have to be able to withstand that temperature. So yeah, one of the key motivation points as we go to these very high temperature reactors is then being able to use that for a hydrogen production plant. So we then go on to some of the other technologies that kind of a bit more of a deviation compared to things that we've seen widespread usage, and this is onto the liquid metal cooled reactor. So the real advantage of going to a liquid metal is the heat transfer potential. So there's much more heat capacity from a liquid than from a gas. I guess as kind of would seem kind of intuitive, there's some complexity in terms of that means you need to make sure that your reactor doesn't go below a certain temperature. You don't want your metal to solidify. And so often these reactors kind of have different emergency heating systems, or you have a certain amount of heat just coming from the fuel, which you can quite readily control. So actually, you can almost get these things to self-regulate. It doesn't have to be kind of external intervention. So one problem is make sure the metal doesn't melt, doesn't solidify. And I guess the other problem then is actually liquid sodium is quite you have to be very careful in your material selection in terms of corrosion. So there can be, if you're not careful, some bad corrosion problems. But we can solve that with the materials we select. And then somewhat analogous then again, you've got liquid lead. So different countries around the world have kind of put their eggs in different baskets in terms of which of these reactor concepts they're really pursuing. So there's kind of a steady set of different reactors being trialled, and the technology being developed in many different countries. And so this link which is at the bottom is to the Gen 4, the GIF, so the Gen 4 International Forum, which is kind of a consortium of countries and researchers that are developing all these different technologies. And I think this might be almost the last one of molten salt reactors. So this is also kind of significantly more sophisticated technology, but has been built. So the US Air Force Research Lab actually had commissioned and had operating molten salt reactors. And it's just a little bit of the misfortune of the time that the program was not able to continue. It was showing promise. So I think that was about 1970s or so, or 1960s even. And there's been a huge revival on that. So there's multiple startup companies. So a colleague of mine now moved to Carios Power in San Francisco. There's multiple startups kind of trying to pursue this technology and take it further, because there's a lot of advantages in terms of neutronics, in terms of thermodynamic efficiency, and in terms of safety. So I think it's one of the things that's quite interesting at the moment. There are multiple startup companies operating in this Gen 4 reactor space. So Bill Gates has put big investments into traveling wave reactors. So there's probably, I guess, definitely tens, if not 20, 30 different startups that are going on. Moltex is one kind of between Canada and the UK, doing these molten salt reactors. And you have two choices in terms of your reactor core can be kind of a more traditional approach, and it can just be that the cooling loop, the external secondary cooling loop is the molten salt, or you can go to a double molten salt process where actually even you could have uranium molten salts in your core. So it depends on how whole hog you want to do, and some very interesting reactor design neutronics calculations, and also some very interesting materials engineering challenges to overcome in terms of the corrosion in molten salts. I guess it's worth highlighting that there's quite a bit of work now in Birmingham looking at molten salts also for concentrated solar power. So molten salts are very effective heat transfer medium. So actually for energy storage, there's quite a lot of interest in molten salts. So these are all very interesting technologies, and they sound nice. And we've got reactor designs, and some of these have been built, but they're not on grid in the same way that we might expect. So all these concepts really are going down a direction of higher operating temperatures. They will have stress and they will have irradiation. And quite often we're also looking into varied and potentially new or aggressive corrosion environments. And this leaves us with a problem, because all our current nuclear materials, they were really designed for 300 degrees C water, or at best they're kind of 550 degrees CO2 of the advanced gas reactors in the UK, where we're principally using graphite and some stainless steels. But really many of these Gen 4 technologies, they want to go to much higher temperatures. So we're talking more like 800 degrees C, potentially even in different irradiation environments if we go to kind of fast reactors, so higher neutron doses. And also we have these issues of corrosion. So this really means that we kind of have these kind of current materials that we're kind of considering for Gen 4. So we can take hopefully the best of what exists from current fission. So we have ferritic martensitic steels, we have stainless steels, we have nickel, graphite and zirconium. But really these exist and are used and demonstrated in a nuclear context from current reactors. But are these going to really meet the demands of Gen 4? So particularly, do they have sufficient high temperature performance, so high temperature strength, high temperature creep resistance, also radiation performance, and also do they have the corrosion resistance? So I think that one is a bit the jury's out in terms of how do we have the material set we need. So actually, I'd say there are materials that could meet many of their demands, but probably not all of them. So we've got kind of next generation high temperature ferritic martensitic steels. We have ferritic martensitic stainless steels, and what is particularly developed towards fusion was reduced activation ferritic martensitic steels. So these take on the demonstration of the materials technology for ferritic martensitic steels and just tailor it and improve it towards these new applications. We have what's determined as outside dispersion strengthened steels. So if you take the fourth year module of radiation material science, you'll see a lot more detail on each of these. We have kind of dedicated lectures on each of these materials. We have refractory alloys, so I spend a lot of my time researching tungsten for fusion, but it also might be interesting for fission. And also in John Binner's group, there's work in the department on silicon carbide. So silicon carbide is particularly pursued for aerospace because it's very lightweight, but it's also quite interesting from the nuclear environment as well. And there's also, I'm a structural materials researcher. I'm sure I could probably do multiple lectures just on the technology of the fuels, but I will leave that to the experts. So the kind of last thing I want to kind of go to on the Gen 4 space, which is kind of halfway between Gen 4 and current generation reactors, and that's what's called advanced technology fuels or accident tolerant fuels, so ATF. There's kind of been a bit of a change and multiple definitions of the name. And this has kind of really been driven by some of the reactor accidents we've seen, so particularly Fukushima Daiichi. Then we've kind of have known this idea that there was a explosion. It wasn't a nuclear explosion, and actually what it was due to is a hydrogen release, and hydrogen expanding and then becoming pressurized. So why do we get hydrogen? And this is the benefit of zirconium is it's got this low neutron cross-section. It's very stable under normal reactor conditions. But one of the unfortunate consequences is when you go to an accident scenario is, especially above 1200 degrees C, you get a change in the reaction between zirconium and water. And actually, what happens is that the zirconium and the water react to create zirconium oxide and hydrogen. And so you get progressively, if you stay in an accident scenario of a reactor, this evolution of hydrogen that's then going to create high quantities. So this is in Unit 1 for Fukushima, then we're talking around 500 kilograms of hydrogen. And the reactor isn't designed to have that quantities of hydrogen. So they tried to outgas it as best they could, but ultimately we had the accidents we saw. And one of the key problems there was, first problem was not being able to get cooling water, but as a consequence of that, we had this accident scenario and the generation of hydrogen. So this is really what kind of these advanced technology fuels seek to solve. So we firstly have a demands to try and have this high temperature stability, way beyond what the normal design, normal operating conditions are. We want to reduce this kind of exothermic nature of this water reaction between zirconium and water that might release hydrogen. And also we just want to increase the grace period. So how long have we got to get, how much time do we have? So one of the challenges, it wasn't just that you have a nuclear accident, you have a tsunami, you have an earthquake. And so it's the other infrastructure around that also needs time in order to be able to make correct decisions. So if you're trying to make a carefully considered decision, if you've got hours and days to make that decision rather than minutes, that gives you a huge advantage in terms of making the right decision. And I guess then, ideally, if you do want to make any changes to the fuel to improve their thermal stability, we don't want to really we ideally would like an economic benefit, or at least no significant detriment. So we don't really want to change the neutron cross-section of the fuel and we really don't want to have to enrich the fuel in order to compensate for a change in the neutron cross-section of the fuel clad. So there's been quite a few different approaches to this. So we could change the geometry of the fuel platelets and how they're cooled. So we could change the reaction design a bit. We could kind of use some evolution materials. So we currently use zirconium. Maybe we could modify that a bit. Maybe we could coat it. There's also ideas of what we could do by doping the fuel itself. And it might be that we could go to a completely new fuel-clad material, or a new fuel material itself. So we could still do this with current reactors and just change the fuel as you do a refueling cycle. So it might be the different types of alloys that you might change for the clad. So in my group in the department, we're working on different steel-based materials. So there's actually a summer internship just advertised, if anyone's interested in that. We also have research projects on zirconium. So trying to develop these new materials that could act as clad as accident tolerance fuels, but also might give us improved temperature capability for Generation 4 reactors. So if you're interested in this research area, then have a look on the school internships page. There's one on there, and also it's something we do master's projects on. And then the same is true if rather than using a metal clad, you could alternatively use ceramic clad. So silicon carbide would be one of the real kind of leaders there. And also we can make some changes to the fuel. So we might look at uranium silicide fuel that's got better accident performance, uranium nitride and uranium boride. And then also maybe we look at something completely different. So maybe we look at composite fuels. So rather than a single fuel, it's got multiple fuels within the fuel thing. We might look at dispersion fuels. So it's not fuel and then clad, that we have kind of a mixed mode of the two. And microencapsulated, so coated particle dispersions, which actually kind of pull a lot from what is used in the space fuels. So for more details, then there's this work from National Nuclear Laboratory. So ultimately, what are these trying to do? Well, they need to tolerate exothermic. I think we've got to repeat there. So I think that's what we call it. So the key thing here was going through what are the demands, what is it we want to meet? So this high temperature capability, how do we meet it? Higher temperature capable materials. And I think that's one of the ideas, and I think something to kind of reiterate when you're kind of trying to do a material selection or materials design, it is this idea of component demands versus material properties. And I hope that's kind of one of the takeaway points from these kind of sets of lectures and is a good lens to put onto for what we have coming in the next couple of lectures. So see you there.